Important inequality relationships exist among the measured parts of a triangle. To establish some of these, we recall and apply some facts from both algebra and geometry. Definition: let A and B be real numbers. A greater than B, read A is greater than B, if and only if there is a positive number P for which A equals B plus P. For instance, 9 is greater than 4 because there is a positive number 5 for which 9 equals 4 plus 5. Because 5 plus 2 equals 7, we also know that 7 is greater than 2, and 7 is greater than 5. In geometry, let collinear points A, B, C on segment AC so that length of AB plus length of BC equals the length of AC. Then, length AC will be greater than length AB, because length BC is a positive number. Each of the 5 statements that follow is called a lemma, lemma 3.5.1. If B is between point A and point C on segment AC, then length of segment AC is greater than length of segment AB, and length of segment AC is greater than length of segment BC. The measure of a line segment is greater than the measure of any of its parts. See Figure 3.45. Lemma 3.5.2. If ray BD separates angle ABC into 2 parts, angle 1 and angle 2, then measure of angle ABC is greater than the measure of angle 1, and the measure of angle ABC is greater than the measure of angle 2. The measure of an angle is greater than the measure of any of its parts. See Figure 3.46. Lemma 3.5.3. If angle 3 is an exterior angle of a triangle, and angle 1 and angle 2 are the non-adjacent interior angles, then measure of angle 3 is greater than the measure of angle 1, and the measure of angle 3 is greater than the measure of angle 2. The measure of an exterior angle of a triangle is greater than the measure of either non-adjacent interior angle. See Figure 3.47. Lemma 3.5.4. In triangle ABC, if angle C is a right angle or an obtuse angle, then measure of angle C is greater than the measure of angle A, and measure of angle C is greater than the measure of angle B. If a triangle contains a right or an obtuse angle, then the measure of this angle is greater than the measure of either of the remaining angles. See Figure 3.48. Lemma 3.5.5. Addition property of inequality. If A is greater than B and C is greater than D, then A plus C is greater than B plus D. Give a paragraph proof for the following problem. Given length AB greater than length CD and length BC greater than length DE. See Figure 3.49. Prove length AC is greater than length CE. Proof: if length AB is greater than length CD and length BC is greater than length DE, then length AB plus length BC is greater than length CD plus length DE by lemma 3.5.5. But length AB plus length BC equals length AC, and length CD plus length DE equals length CE by the segment addition postulate. Using substitution, it follows that length AC is greater than length CE. Theorem 3.5.6. If one side of a triangle is longer than a second side, then the measure of the angle opposite the longer side is greater than the measure of the angle opposite the shorter side. The relationship described in Theorem 3.5.6 extends, of course, to all sides and all angles of a triangle. That is, the largest of the 3 angles of the triangle is opposite the longest side, and the smallest angle is the opposite the shortest side. Consider Figure 3.52, in which measure of angle A equals 80 degrees, and the measure of angle B equals 40 degrees. It appears that the longer side lies opposite the larger angle. That is, it appears that length of BC is greater than the length of AC. Theorem 3.5.7. If the measure of one angle of a triangle is greater than the measure of a second angle, then the side opposite the larger angle is longer than the side opposite the smaller angle. The following corollary is a consequence of Theorem 3.5.7. Corollary 3.5.8. The perpendicular line segment from a point to a line is the shortest line segment that can be drawn from the point to the line. In Figure 3.54, PD is less than PE, PD is less than PF, and PD is less than PG. In every case, segment PD is opposite an acute angle of a triangle, whereas the second segment is always opposite a right angle, necessarily the largest angle of the triangle involved. With segment PD perpendicular to line L, we say that PD is the distance from point P to line L. Corollary 3.5.8 can easily be extended to 3 dimensions. Corollary 3.5.9. The perpendicular line segment from a point to a plane is the shortest line segment that can be drawn from the point to the plane. In Figure 3.55, segment PD is a leg of each right triangle shown. With segment PE the hypotenuse of triangle PDE, segment PF the hypotenuse of triangle PDF, and segment PG the hypotenuse of triangle PDG, the length of segment PD is less than that of segment PE, PF, PG, or any other line segment joining point P to a point in plane R. The length of segment PD is known as the distance from point P to plane R. Our final theorem shows that no side of a triangle can have a length greater than or equal to the sum of the lengths of the other two sides. Theorem 3.5.10 is often called the triangle inequality. See Figure 3.56. Theorem 3.5.10, Triangle Inequality. The sum of the lengths of any two sides of a triangle is greater than the length of the third side. The following statement is an alternative and expanded form of Theorem 3.5.10. If A, B, and C are the lengths of the sides of a triangle, and C is the length of any side, then A minus B must be less than C, which must be less than A plus B. Theorem 3.5.10, Triangle Inequality. The length of any side of a triangle must lie between the sum and difference of the lengths of the other two sides.